Hello students, in this session we are going to study the strain energy due to bending. When a bending moment is applied on a beam, what is the strain energy stored due to that bending moment, right? So let us have a beam, we have a beam like this. It has some length, say L length beam is there. It has some length L. And we want to find out, due to some bending moment applied due to certain type of loading, whatever type of loading is there, whatever type of supports are there, what is the strain energy stored in this material due to this loading, right? So what we can do is we can take, because the bending moment is changing, so we can take a small length say dx, in this case small length dx, assuming that the bending moment is not changing in this part dx, right? Bending moment is not changing in this part dx, but the bending stress is changing. Bending stress is changing above and below the neutral axis, because bending stresses are not uniform throughout this section dx. Above the neutral axis, at neutral axis it is 0 bending stresses, and above the neutral axis it is increasing and maximum at the outer fiber. You already know that bending stresses. Go to the bending moment diagram chapter and you will get this type of curve. This type of curve you will get, that bending stresses are not uniform, they are varying, right? They are changing and they are maximum at the outer fiber and 0 at the neutral layer, right? So what we can do, because the stresses are varying, so what we can do is, in this, and we have taken a small length dx, so we have to find out this what is the strain energy stored in this small length dx, and then that will be integrated to get the total strain energy stored in this beam. But still stress is not uniform, stress is varying, so we can take a further small section above the neutral axis. Say this is a section, a strip, this strip, right? And suppose this section which we have taken, this section which we have taken, this is suppose A, B, C, D, and in this we have taken a small strip, this small strip P, Q, R, S, at a distance y, from the neutral axis, and it has a thickness of dy, right? A small thickness strip is taken PQRS. So, and assuming that the stress is uniform in this part PQRS, right? So we have taken two times the small sections. One, we have taken a small length dx, integrating this, and we will find out the strain energy in this dx. Integrating this, we will get the total strain energy in the beam. And in this also, we have taken a further small volume PQRS. This small volume PQRS has certain width inside the board and thickness dx, strip again thickness dy, and width inside the board, say some width is given. Suppose it has a width b, it has a certain width inside the board, b width inside the board. So what is the volume of this strip PQRS? So volume of PQRS will be equal to dx dy b, dx dy multiplied by b. And what is dy multiplied by b? This is the area multiplied by length. So this is equal to dx multiplied by dA, right? So this is the volume of this strip PQRS, and in this volume PQRS some stress is developing sigma, and we are assuming that stress is uniform and also bending moment is uniform. So now we can find out the strain energy stored in PQRS, that can be integrated to get the strain energy in this ABCD, and that can be integrated to get the strain energy in the entire beam, right? We have to do 2 times integration. So first find out the strain energy in PQRS. So strain energy stored in PQRS, this volume. What is the strain energy stored in this volume PQRS, right, which has certain width B inside? So that is the strain energy stored will be equal to sigma square upon 2E. This formula we have already derived, multiplied by the volume PQRS, volume of PQRS. This we have already derived, that if the stress is uniform like in direct stresses, the strain energy stored is given by sigma square upon 2E multiplied by the volume of this PQRS, right? We can further write here what is the bending equation. Bending equation, how to find out sigma, bending stress, that is from the bending equation. Bending equation, it is known to us, bending equation, that m by I, m is uniform now, sigma by y for this part dx, sigma by y E by r. So from here we can find out sigma as my by I, my by I, right? Now we can put here that is equal to sigma square m square y square by 2e I square multiplied by the volume. Volume of PQRS is dx multiplied by dA. So dx multiplied by dA, right? So this is the strain energy stored in this PQRS volume. So we can further write m square dx upon 2e I square y square dA. Now it can be integrated. It can be integrated to find out the total strain energy stored in this strip dx, right, in this part of the beam dx ABCD. So strain energy stored in ABCD, which is a small part of the total length. Strain energy stored in ABCD, in volume ABCD. So what is the strain energy stored? And it is a small part of the total length dl. L length, this is a small part dx. So and dx is constant, right, in this part. So we can write integrating this, we will get the total strain energy stored in this ABCD. First we have found out the strain energy in PQRS. Integrating this, we will get the strain energy in ABCD, and dx is constant and m is also constant. So we will get m square dx upon 2e I square multiplied by integration of y square dA. And what is this y square dA? This is the second moment of area. So integration of y square dA is second moment of area, and it is also called moment of inertia, area moment of inertia. So this is the moment of inertia basically I. So this is basically I. So we can write I and I, one I will be cancelled out. So m square dx upon 2ei. This is the small strain energy stored in this part ABCD. Now what is the total strain energy stored in this material? Further integrate it. So total strain energy stored in this beam will be integration of m square dx upon 2ei for the entire length from 0 to L, right, starting from certain length 0 to total length L. So this is the strain energy stored in the beam m square dx upon 2ei. Now if m is constant, this is the case when m is variable, right? M for dx we have taken the constant m, but for entire beam there will be different m. So if m is constant, then what is going to happen? If m is constant, then what is the case? In that case the integration of dx will be L. So u will be equal to m square L upon 2ei. So this is the total strain energy stored when m is constant. for the entire beam, right? For this part we have taken m constant here, right? But for entire beam it is variable, that's why it is inside the integration part, right? So this is the strain energy stored in the bending, right? How we have done this? We have taken a beam. In this beam of total length L, we have taken a small length dx, but in this dx length the stress was not uniform. We have further taken a small section PQRS where the stress was uniform, assuming that the stress in PQRS is uniform. The volume of the PQRS was dx dy multiplied by the width b. It is a rectangular section having a width b. So dx multiplied by dA is the volume of this part. Now we know the strain energy is given by when the stress is constant is sigma square upon 2e multiplied by the volume. So this is the strain energy stored in PQRS, this small strip volume PQRS. So sigma is given by the bending equation, that my by I. We have put here my by I dx dA. We have got this equation. Then what is the strain energy stored in this length dx, small length dx, entire section above and below the neutral axis. So this can be integrated, this part PQRS can be integrated to get the strain energy in ABCD. So this is the strain energy stored. M is constant, we are assuming M is constant for this part, not for entire beam, for this part only, and dx is also constant. So M and dx taken out and we have got y square dA integration, which is the second moment of inertia or second moment of area. So this is the moment of inertia. So we have got m square dx upon 2ei. This can be further integrated from 0 to L to get the total strain energy stored in the entire beam. So total strain energy stored in entire beam is m square dx upon 2ei from 0 to L. And if m is constant, then we can find out the strain energy stored as m square L upon 2ei. So this is how we can find out the strain energy stored in bending.